Hello again. I am Dr. Jade Mitchell, and this is part two of the module Cost Benefit Analysis and Decision Trees. In the first part of this module, we learned to structure a cost benefit analysis using a decision tree. In the second part of this module, we will we'll discuss how we will use a decision tree when there's no bright line or threshold, like 1 in 10,000 illnesses or infections per year, to base a decision about whether we need to implement a risk management strategy or not. And this is the case for many risk assessment problems that are conducted. So, using our decision tree that we discussed in the last module, we are going to evaluate our cost benefit analysis or sketch it out graphically using the same formal structure. And then we're going to solve our decision problems using that structure. Our chance node again is the uncertain event. And for QMRA, those uncertain events or probabilities are the same values that you're calculating in your risk assessment, and generally will be the probability of infection, the probability of illness, or the probability of death. And then the decision nodes that we're making are going to represent what choices the decision maker is making about how to mitigate the risk for the pathogen. For example, it might be administering a vaccine or some other medical countermeasure. It may also be environmental decontamination to different levels or setting standards as described in the previous example on marginal cost effectiveness. So let's consider a tree where we are deciding whether to administer a vaccine or not, or some equivalent countermeasure. There's a probability, yes, of death if we administer the vaccine, and there's also a probability that the person does not die, or a person does not die. We can assign the probability of death as Q, and the probability of not dying if we administer the vaccine as the complement 1 minus Q. The cost for our outcome if a person dies or if the administration of the vaccine results in death would be the cost of the vaccine itself plus the value of a statistical life if we're using VSL as our metric. If no death occurs, we only have a cost for this outcome equivalent to the cost of the vaccine. Again, if we decide not to administer the vaccine, there is still a chance of death. And if the chance of death is defined as P, then the chance of no death is defined as 1 minus P. For no death and not administering the vaccine, there's no cost. So $0. If there is death and we did not administer the vaccine, then the cost is just the value of the statistical life that was lost. So now we can suppose that we know what Q is, and we might want to ask, how high does P have to be to justify providing the vaccine? So in this case, we've done a risk assessment and we might have probabilities, so we have Q, but there's no bright line. There's no 1 in 10,000 or 1 in a million to make the comparison with. We need to calculate from our cost benefit analysis what probability of this outcome justifies the action that we're considering. In this case, the action is administering the vaccine. So in order to do this, we're going to extrapolate upon the general governing equation for calculating expected value, which will be the sum of all the probabilities times the outcomes. The expected value for vaccination will then be equivalent to Q times the value of the statistical life plus the vaccine, plus 1 minus Q times the cost of the vaccine. The cost associated with no vaccine is just going to be P times the value of life. Recall that in the no vaccine case, if there was no death and it wasn't administered, then there was no cost. So we just have one term in the expected value equation for no vaccine. And this is how we would set up a problem where there's no threshold. We can set these two terms equivalent to themselves, which I'll show in the next example, and then calculate for the p-value that we're looking for. So in the next example, again, an arsenic in drinking water example, our option is to install a point of use device at a household with a single resident. And this just simplifies our calculations to one life. We know that this point of use device will remove 90% of the arsenic. And we can assume that its efficacy is equivalent to 90% because of this. So here our decision is to install the point of use device. If we do it, yes, there's a chance of death. And we can define the chance of death if we install it as 0.1 times P. We're multiplying by 0.1 because recall that we're removing 90% of the arsenic, and that's the efficacy of this particular treatment on reducing the risk. So if there is a death and we installed it, our cost is going to be the cost of the point of use device, which we assign as $2,007, plus the value of the statistical life, which from this study we assign as $6 million. If there's no death, our probability is going to be the complement, which is going to be 1 minus 0.1 times P. And the cost here will only be the treatment cost since there's no resulting death. We can do the same thing for the bottom of our tree. If we do not install the point of use device, there is still a probability of death. If it occurs, the probability is equivalent to P, and the outcome is $6 million for the value of the statistical life. If it does not occur, the probability is 1 minus P, and there is no cost. So now we can calculate how high P has to be to justify using the point of use device. As I mentioned, we extrapolate from our general equation where we multiply each probability by each outcome. So for the treatment, the point of use device, we had $2,007 times 1 minus 0.1 times P. Oops. Plus 0.1 times P times 6,002,007. For no treatment, the cost here is just the single term, P times $6 million. So in order to calculate the value for P, we're going to set these two equivalent values equal to each other because now we have two equations with one unknown. So we're going to set P times 6,000 equivalent to the expected value equation that we just derived for the treatment. And when we do the math here, we find that P is equivalent to 0.00037, or 4 times 10 to the minus 4. So this gives us a value that is a risk of death that can now be used to evaluate a decision about whether we're going to install the point of use device or whatever the risk management strategy will be. We can apply our risk assessment framework to go back and look at dose and environmental concentration, etc., to determine what corresponds with this risk as well. So in order to interpret these results, we found that our P was 0.00037 or 3.7 in 10,000. We wouldn't necessarily say that it's acceptable, though it's the value based on the cost-benefit analysis that was conducted that justifies implementing your risk management strategy. One might say something like a risk below 3.7 in 10,000 would not merit mitigation based on a benefit cost analysis with assumptions of the analysis detailed in the attached report. And then you would provide all of the details of the cost benefit analysis that was conducted in that report. And the reason why you wouldn't use the term acceptable is because acceptable or acceptability is based on values, which were previously discussed in Dr. Gurian's presentation on valuing risk. And also because we know that not everything is captured in a cost benefit analysis. Say if we were looking at doing a similar approach for a food industry, that industry might, if there's an outbreak or a recall, the result might also be lack of trust or lack of sales. So there are other costs, some tangible, some intangible, that are not incorporated in the cost benefit analysis directly, and therefore not included in the calculation of which value would justify the risk management strategy. So this concludes this part of the module, and now you know how to structure your cost benefit analysis as a decision tree, and then also use that decision tree in order to calculate a threshold when a bright line approach does not exist. So here, oops, that's the wrong slide. I'll stop here.